Okay, well, let's try going over the practice exam solutions here. So number one, we have to draw a disconnected graph with these vertices, or explain why it's impossible. So one thing we can do first is just add these up, these degrees of each vertex. So we'd have 2 plus 3 plus 3 plus 3 plus 3, and that would give us 14. If that number would be odd, it would be impossible to draw any kind of graph because the total edges of any graph need to be even. So that would be a good reason why it'd be impossible, but in this case it is even, which doesn't, well, anyway, let's go ahead and go into this. So there's many possible solutions. Notice that these numbers here on my vertices are the degree of that particular vertex. So I just set up these. I know that this is a complete graph with 4 vertices, which means each one will be connected to 3 others. That leaves me with a 2 I need to pick up and draw it over here so that it is disconnected. Okay, in a simple graph, originally I hadn't written simple here, and in that case it would be disprove. But in a simple graph, in other words, no loops and no parallel edges with n vertices, there must be at least 2 vertices that have the same degree. And you may convince yourself of this more by start off with, for example, 3 vertices, and you know that the highest degree would be 2, right? Because in a simple graph, we're not going to loop to itself, so the most it can do is connect with everyone else, which would be n minus 1. So theoretically, we could have 0, 1, and 2 for a graph with 3 vertices. However, if one of the vertices had degree of 2, it connects with everything else. If one of the vertices has a degree of 0, it doesn't connect with anything. So those two are going to create a contradiction, which is what I explain here. And I explained it in the general sense, but again, I would highly recommend you choosing a few small, concrete examples to start off with to kind of convince yourself or come up with a pattern. Okay, connected graph with 5 vertices. Most important thing is that we don't have an Euler circuit and we don't have a Hamiltonian circuit. Notice that when we have this kind of, well, a Hamiltonian circuit, we can't return to any vertex. So anytime you have the graph kind of divided in sections with vertices like this, or if the only way to get through a vertex and it has a degree higher than 2, we know that that's not going to work out either, because we can't return to the vertex once we've already left it in a Hamiltonian circuit. Now, in a Euler circuit, we could, but the problem is here we can't get back to that central vertex without going along an edge more than once. Okay, prove or disprove. So this is using the concept of a tree, basically. So a tree is the minimal connected graph, and we know that a tree has 1 less edges than it does vertices. So if we tried to get even fewer edges than n minus 1, we're going to break the connection somewhere. We remove another edge, we're not going to have a connected graph anymore. Now, if we had a circuit and we removed an edge, we could still have a connected graph. In fact, if we have a circuit, there will always be at least 1 edge that we can remove and still have a connected graph. And then when we remove that, we either have a graph that doesn't have any circuits, so it's a tree, or maybe there still are circuits. And as long as we have circuits, there's always at least 1 edge that can be removed until we get down to a tree. Once we get to a tree, we can't remove any more edges. Okay, number 5. Again, lots of possibilities here. the main point that I'm trying to drive home here is when you see a question about graphs, ask yourself, could I answer this with a connected graph or a disconnected graph, circuit-free graph, or a graph with circuits? Are loops allowed? Are parallel edges? I want you to be thinking about these different possibilities of a graph instead of just limiting to a kind of standard graph, like, for example, this one. Okay, so we need a disconnected graph. Otherwise, if it's connected and it has one less edge than it has vertices, it's guaranteed to be a tree. So we need to make sure that it's disconnected. Okay, 6, now we have some weights. So instead of just having vertices, each edge has a weight associated with it. You could use, for example, you could pick any vertex and use Prim's algorithm, or you could use the Kruskal's algorithm, which I think is what I use. Just choose the smallest weight. Here you have a choice of 3. Choose any of them. Get another one. So we get these 3 edges right here. We cannot take any of the 5s. If we choose any one of those 5s, we're going to increase the weight of our graph, the total weight, to more than 12. Okay, that was a pretty ugly copy of the map. The dual graph, so here notice that each of the countries has a vertex and they're connected if they border. Notice also that the Philippines is an island country, and I said to assume that countries that are separated by water do not border. So if it's only an island country, it will not be connected to any other countries. So here we have it. Notice that as soon as I see this triangle here, as soon as I see that, that's called K3. That's the complete graph with 3 vertices. As soon as I see that, I know that my chromatic number is going to be at least 3. If I saw a connection here, for example, I would have K4. So I know my chromatic number would be at least 4. That's not the only way, but it is certainly a one quick way to know a minimum number that chromatic number can be. Now the question is it more than 3? So I know that it's not going to be more than 4 by the 4-color theorem, that any planar graph, any plane graph can be colored by no more than 4 colors. But do I need 4? So I start off, I go ahead and give these 3 distinct colors. After I do that, I only have one option left for Cambodia, because it has to be, if I'm trying to do minimum colors, I can't use the Thailand color and I can't use the Laos color, but I can use the Burma color. And then once I do that, Vietnam has to get the same color as Thailand. Malaysia could be 1 or 2. Brunei and Singapore just have to be different ones, so we might as well color them with the same as 1 and 2. And Philippines and Indonesia can each get any of the 3 colors. So it is certainly possible to color it with 3 colors. And then to raise the chromatic number, again, I'm looking for, is there a place where I can make K4, where I can have 4 vertices that are all connected to each other? And there is right there. Burma and Cambodia would make it so these 4 vertices are all connected. Now how would you do that in real life? I don't know, create a land bridge between Burma and Cambodia, or an underground tunnel or something? That's a bit more difficult of a question. And then I just put this in here, the geographic mistakes, because I think it was unfortunate that they did put Singapore here as this large chunk of an island, which is completely false. Singapore is a little island country right down here on the tip of Malaysia, and Brunei doesn't take off all of this because Malaysia has another section here. I believe this is Indonesia, actually, another section. So if you drew it correctly, the plane graph would actually look different also. Okay, number 8. No more than 8 vertices that has a chromatic number of 6. Well, we know that the smallest graph with a chromatic number of 6 is going to be K6, and that certainly would have less than 8 vertices. So I go ahead and draw that. If you didn't do that, you could get more complicated really quick. You certainly can't have less than 6, and if you do have 6, the only way to get a chromatic number of 6 is if you have K6. Otherwise, there's 2 vertices that aren't connected to each other, so those could be colored the same color. Now, if you had 7, there'd be a few more ways to do it, and 8 would be even more ways to do it, but this is certainly the simplest way. So the key takeaway point here is just keep in mind that that complete graph of order n has a chromatic number of n, and it's the simplest graph with the chromatic number of n. Okay, and finally, the following algorithm segment. So we have a loop within a loop. I always like to start off with the actual calculation step or steps and figure out how many calculations there are per loop, and then I go and figure out how many loops there are. So right here, just think as you would actually do this problem. We need to multiply 2 by I first, then we subtract that from n, and finally we square it. So 3 different calculations there every time we run through this loop. And now let's just draw a quick graph of what's going on here. So I is going from 2 to n, so let's make all those different categories. And within each I, j is going from I to n. So let's start within this first column. If I is 2, then j would be going from 2 to n. So I write out j equals 2, 3, all the way down to n. And there's n minus 1 of those. There would be n, except we don't have j equals 1. So we have to subtract that from the n possible. So there's n minus 1 loops here when I equals 2. When I equals 3, j is only going to go from 3 to n. So we're going to start off at 3, go down to n. Notice that we'll have 1 less than we did in the previous column, so we'll have n minus 2 loops there. Continuing that pattern, the final value of I would be n. So when I does equal n, notice that j is going from n to n. In other words, there's only one value of j equals n. So that equals 1. And you can see that these column, number of loops per column is going to go down one by one until it reaches 1. So now we have to ask ourselves, how can we total this up? We need to total all the numbers 1 through n minus 1. We want to sum them all up. So I'm just going to write it like this. I'm going to use our formula. This is it's the same formula we're used to, except we usually go from I equals 1 to n. Notice that I'm still doing that same formula. It's just my lower number is n minus 1, and then when I add 1, I get n. You could change one of these variables to something like k if that helped you see better what I did here. Essentially, I replaced the n that we usually have by n minus 1. So then n got replaced by n minus 1, n plus 1 got replaced by n here. And all gives us this formula here. So we do have to multiply that total number of loops by the calculations per loop, which is 3. Multiply that all out, you get 3/2 n squared minus n, which would have theta of n squared. That would be on the order of theta n squared. Okay, let me know if you have questions.